Now we can define several things. First, we define vectors of functions. G dimensional vector of functions. For example, this, I think of this as a transpose. I can write function phi of x. I can write it as phi evaluated on the fundamental domain, phi evaluated on the first image, G1 of fundamental domain, a finite number of components. So I just split it. It's a function that I had over the whole space, but I just write it as a set of function values on the domain. Or I can define fa of x to be value of the function any place on the space obtained by starting with a point in fundamental domain and looking at its image under A. So these are components of this vector. Then I can write this thing that I have there. I can write delta y minus. And now I'll define a map that only stays within the fundamental domain. So I'll define f tilde. And this applies only if C is A, B minus 1. So product of these two operations is the relative distance between whatever the original points are, where fx tilde is defined as C, this combination of group operation f tilde. So what this thing does is, by definition, it keeps us in a fundamental domain. Where you really are in a big space is tracked by this C operation that puts me there. This Kronecker delta, this is some kind of matrix, and that matrix has a name in theory representations of finite groups. This is called left regular. Mostly you don't have to worry about whether it's left or right, but sometimes you do, of discrete group G. In crystallography, quantum mechanics, etc., they tend to use letter D for this kind of matrix. For group operation C, this is a matrix whose two labels are these guys here. It's just a matrix of zeros and ones. It's 1 if any point in the fundamental domain under evolution ends in tiles and 0 otherwise. So in general, when you have, let's say, 9 elements, most you can do with them is permute them in all possible ways. So group G is always a subgroup or equal to symmetric group of permutation on G elements. And this is instructing you in how the permutation works on any two tiles. So the simplest example that we did last time was symmetrization of dihedral group D1, which is a group with two elements. Either you do nothing, that's identity, or you flip, rotate or something. This property that sigma square equals 1. That's a very simple group, so it has only two elements. So this matrix is 2 by 2 matrix. And D of the identity says do nothing. So the identity is 1, 1, 0, 0. So that meant that both A and B were identity because I was in the same domain. I didn't exit from the domain. Or I went into the second domain. This was a world in which I had fundamental domain and its reflection, sigma. Fundamental domain, whole state space. And the other element, D of sigma, what it does is just permutes the two elements. One. To summarize, if dynamics is equivariant under discrete symmetry, then evolution operator can be always written as a matrix whose elements are not one, but the element is the dynamics within the tile, but correctly placed by this element C in the big space, relative space.